Hi, welcome to Lecture 2. So in Lecture 2, we're going to talk about the language and the basic concepts of Bayesian statistics. Now, we began talking about many of these concepts in Lecture 1, so if you haven't watched that video, you'll certainly want to start there. Now, after you've watched Lecture 1, you might recall that one of the big subjects in that lecture was this so-called therapeutic touch experiment. This is the famous, quote, Emily Rosa experiment from the late 90s. The idea was that practitioners of therapeutic touch were placed behind an occluding screen with their hands through a slot, and then the experimenter would randomly select a hand to hold her hand above, not touching, but just slightly suspended above. And the idea was that the practitioner was supposed to select which of their two hands, left or right, was being indicated by the experimenter. And so this was a simple experiment to do. In all, Rosa did 280 trials, and overall, the therapeutic touch practitioners exhibited 123 successes. So that was around 44% or so. And so we used this example in Lecture 1 to motivate the idea of statistical inference, particularly classical statistical inference. And we used this framework to look at that method, if you will, of doing statistical inference. There are these three sort of pillars of statistical inference that we must use. One is we describe the observed data. So of course we just did that. That's 123 successes out of 280 trials. And then to make sense of that data and in turn answer a scientific question, namely, are these therapeutic touch practitioners simply guessing, or is there really a better than chance ability that they have? To do that, we have to define some statistical models and then do some estimation and model comparison to see which model best supports the data. So what we did in Lecture 1 was we developed the so-called binomial model. The binomial model simply links the idea of counting successes out of binary trials to the probability of getting a certain number of successes. It has one parameter, so it's a really simple model. That parameter is W, and remember, W represents the probability of success on any one trial. The idea is we've observed some data. We now want to know what is the value of W that is in this sort of population of therapeutic touch practitioners. Now, the null hypothesis, the one that would suppose there really is no effect going on here, it's purely chance, the null hypothesis would specify precisely that that parameter W is equal to 0.5. That is, there is a 50-50 chance of getting a success on any one trial. Whereas the alternative hypothesis, the one that would say there is something going on with therapeutic touch, that would specify that W is bigger than 0.5. We don't know exactly how big, but certainly better than chance. And the way that we concluded Lecture 1 was to develop the what's called binomial test. And you can see over here the R code snippet from what we did. We found, and sorry, this is covering up. Let me make that to where it's visible. We found that to get 123 successes, the p-value that resulted from that test was 0.9819. And so that means that those observed data are reasonably plausible, in fact, really plausible, under the null hypothesis. And so we did not reject the null, which left sort of a question. If you can't reject the null, what can you conclude? The answer turns out to be not much, but we certainly did not find an effect. We did not reject that null hypothesis. We did not support this model. So in the end, from our classical results, all we did was I should even cross that out, really, because as a Bayesian, I know that the story is much more complicated than this. But the basic idea is we were not able to rule out this hypothesis. So that's what we were left with. Now, the question that I sort of alluded to at the end of that lecture was, what can we do with this? What can we do with this p-value? Is it at all diagnostic? So I posed that question to begin our lecture today. And that is, what does this p-value, 0.9819, represent? And the answer, sadly, is that it's probably not representing what you think it does. So let's talk about why that's the case. Well, first of all, we need to go back and look at some what you would call misconceptions about p-values. Now, these aren't just things that I think people get wrong. These are documented in the literature. You can see Gerd Gigerenzer's paper in 2004. It's got the great title, Mindless Statistics. If you just Google that, you'll find this paper. One of the misconceptions that people often bring to the table about p-values is that the p-value somehow represents the probability that the null hypothesis is true. This is simply not the case. And of course, by extension, they often think that 1 minus p is the probability that the alternative hypothesis is true. Again, this is not true. These are just simply not a true statement. And there are many others similar to this. Now you might be wondering, well, I had those misconceptions, so does that mean that I just don't know what I'm doing? Is there something wrong with me? And the answer is, well, don't think that way, because it turns out that even though these are all incorrect, they are very widely believed to be true by students and professors alike. So people who have had multiple statistics courses and ostensibly do this sort of thing for a living hold these misconceptions. You can see that while 100% of their sample of psychology students got answers incorrect out of that list, 90% of professors and lecturers not teaching statistics and 80% of those who do teach statistics got some of those things incorrect. So don't feel bad if you thought that any one of these statements up here was true. The fact is, though, that they're not true, and that's one of the things that we're going to use to motivate our study of Bayesian statistics. So what is a p-value? If this is not what it is, I mean, wouldn't that be really nice? But it's not. So what is it? Well, let's look at the definition. So the definition of a p-value is it is the probability of observing data, or more extreme, if the null hypothesis is true. It's a conditional probability. Now, sometimes I write it this way. This is a blatant abuse of notation, as you're going to see later in today's lecture. I will use this notation to represent something quite different. But if you want to think about it conceptually, it is the probability of observing some data given that the null hypothesis is true. Now, that's fine, but it doesn't give us what we often want as scientists. What we want to know is our theory right? You know, it'd be really good to know what's the probability of that null hypothesis, or maybe even an alternative hypothesis, given the data, right? As scientists, we observe data and we want to use that to infer about the models, the hypotheses that we put forth. So wouldn't it be nice to be able to know that probability? And I think it is, but to do that, we can't get it from the p-value directly. We've got to use something called Bayes' theorem. So that's what we're going to talk about today. Now, I could spend an entire lecture giving you a lot of the history and development of Bayes' theorem. I'll just say really quickly, it's a very old theorem. It comes from the 1600s. Reverend Thomas Bayes, theologian, amateur mathematician by all means, came up with this. It's a reasonably simple concept to prove, but it's incredibly useful in statistics. It's incredibly useful for the kinds of problems that we care about. I would invite you, I'll put a link in the description below to a really nice introduction to Bayesian thinking and Bayes' theorem itself by the YouTube creator 3Blue1Brown. Does amazing mathematical visualization videos, so I'll put a link down there. That one will give you a lot of the background on Bayes' theorem. For us, the way I like to think about Bayes' theorem is written in this form. So it says that the probability of a hypothesis H given some data is equal to the probability of that hypothesis times the probability of the data given the hypothesis divided by the probability of the data. Now, in symbols, this is probably not very elucidating right now, so let's talk about what each of these components means so that we can come up with an easier way to remember Bayes' theorem, and I promise you, it's very easy to remember. So let's look at these components from left to right. The first component, this probability of H given data, this is called the posterior, okay? It's posterior because it's the degree of belief in the hypothesis after observing data, okay? So posterior means after you've observed the data. So this is kind of, as scientists, what we want to know. After we've observed some data, what's the probability that my hypothesis is true? Now let's go to the next one to the right. This symbol P of H, this is called the prior. Prior is simply the degree of belief in the model before observing the data. Now this is interesting, right? Notice it does not have that conditional on data statement. So this is how much you believe in the model before you see the data. And then the posterior, this guy, is how much you believe in the model after seeing the data. Now, one of the neat things about Bayesian statistics is it's all based on this formula, which basically says my degree of belief after seeing data is equal to the degree of belief before seeing data times something, times an updating factor. So what exactly is that updating factor? Well, let's look at those two components. That one up top, I'm going to get them all on the same screen here. This one, the probability of data given H, it looks kind of like the way I wrote the p-value earlier, but it's not. It's not quite the same thing. But it is called the likelihood. This is something we've talked about before. This is the degree to which the observed data is likely under the model, right? It's the reverse of the posterior. And then finally, that thing at the bottom, I'm going to mention what it is. You'll find out that we often don't really care about this, and you'll see why a little bit later. I'll try to remember to bring that up. But it's given lots of names. Sometimes it's called the evidence. I don't particularly care for that name because I like to use evidence in a slightly different context. In others, you'll see it called the prior predictive. Essentially, all it is it's a weighted average of the probabilities of observing data under all models being considered. Let me highlight that. Okay. And so essentially what it gives you then is that it means that this updating factor that we see here basically says how well the data fits this model compared to all the other models. And so if it fits it relatively better than the other models, it's going to increase your belief in that specific model because this fraction is going to be bigger than 1, right? So if that didn't make sense, you can rewind it and listen again, or you can frankly simply ignore it right now. The basic idea that we need to remember right now is that Bayes' theorem looks like this. It says that the posterior is proportional to the prior times the likelihood. And I say proportional to because it's not exactly equal, right? You've got to divide by that prior predictive thing. But throw that out, it's proportional to the prior times the likelihood. So that's the big concept. That's what Bayes' theorem gives us to do scientific inference with. So let's see what we can do with this. Why do we care, first of all? Well, remember from lecture 1, we conceptualized inference as the following problem. Given some data, right, we're scientists, we observe data, what is the parameter in the model that gave you, that would have given you that data, right? You're searching for the unknown that you can't see up here in the cloud. So let's suppose, let's have something that's similar to the Emily Rosa experiment, but with a smaller number of trials. Let's suppose that we observed 9 successes in 20 trials. That's a success rate of 45%. So we might ask the question, what is a reasonable range of values for this parameter W? That's what we want to do. That's the kind of inference we want to perform. Well, last time we did this by plotting this so-called likelihood function. So remember, there was a code chunk from R to do that. And we got basically, once we observed a certain amount of successes, okay. Now this was last time, it's a slightly different problem, but this is what we got. We were able to get a maximum likelihood estimate. This was the point at which we had the most likely value of that parameter W. Okay, the W ranges from 0 to 1, of course, because it's simply a probability. The most likely value is this. Here's the thing, though. So why is this not good enough for the types of problems we want to consider? Well, first of all, it's not a probability distribution. And the reason for this is simply if you were to somehow compute all of the area under this curve, and you can do that using tools from calculus, specifically integration is what we would use. If you were to calculate the area under that curve, it's not equal to 1. And that's what you have to have a probability distribution. You have to have it equal to 1. Now that's a technical point, but it's a very important technical point because without that, it's really hard to quantify our uncertainty in this estimate of W. Remember, this is the most likely value of W because it has the highest likelihood. But I mean, our estimate ranges completely from 0 to 1. Now 0 up to about here is not very likely, but there is some positive likelihood that we need to take into account somehow when we're quantifying our estimate of W. So because it's hard to quantify that uncertainty, this is a relatively difficult way to do this. Particularly what I would like is a statement like this. I would like to say there is a 95% probability that W is between this value and this value. You know, maybe it's from here to here, I don't know. But again, I can't do that easily with this because it is not a probability distribution. So what do we do? Well, Bayes' theorem helps us, right? What we need is something that is a probability distribution. Particularly, we need a posterior distribution. We need a probability distribution that says, after seeing the data, here's our relative belief in this model, in these values for W. And Bayes' theorem gives us this. It gives us the mathematical tools to transform this likelihood function into a probability distribution. Because how does that work? Well, remember, the posterior comes from, it's proportional to the prior times the likelihood. Okay. Now, we already have the likelihood function, right? We did that in lecture 1. That's that binomial function. In R, it was called d binom. The only thing missing is that we need a prior. So it would help if we talked about what priors were and how to use them in order to get this posterior distribution. So let's go there. So what is a prior? Well, in this context, what we are talking about when we mention a prior is we are talking about a probability distribution that mathematically encodes our prior belief about the model parameter in question. Now, I want to give you an example. Actually, I'm going to give you 3 examples of priors that we could use for this problem. Priors give us a degree of choice as the analyst, right? Everyone could potentially have their own prior. So let's see what that flexibility does to our inference. Okay. So let's look at these 3 different priors. The first prior that I'm going to look at, it's a very common one actually. I'm going to call it the uniform prior. Now I want to be real clear, the names that I'm going to give these priors are simply so that we have something concrete to discuss. They're not standard names, although this one kind of is. It's called a uniform distribution, but sometimes you'll see it called a slab distribution or a flat prior, things like that. So I'm going to call it a uniform prior. So what is a uniform prior? Well, it's literally flat, okay? It is a probability distribution that says that every value of W across the spectrum from 0 to 1 is equally likely. Let me highlight that. That's important. And what this represents is an analyst who has no strong prior belief in any range of values for W, right? They don't think that bigger values of W are more likely than smaller values or vice versa, or that these middle values are more likely than the outside values. No, it represents the idea that every value is equally likely, okay? So it's called a diffuse or flat or uniform prior. Okay. Now, is that a good prior? Well, I don't know. We'll talk about that in just a second. Here's another prior that we could use. Okay. I'm going to call this one a sharp peaked prior. This is not the name. I mean, this is just one that I came up with for this lecture, but I think it reasonably represents the geometry of this prior. Again, we have a probability distribution. If you calculated this, the area under that curve, that straight lined curve, is exactly 1. Okay. What this prior says, if you look at it, is that the most likely value a priori, again, before seeing data, is W equals 0.5, right? And you'll notice here at 0.5, the peak is right there. So if you are a skeptic, and remember the whole context here is therapeutic touch a thing? Are people guessing or not? Well, if you're a skeptic, you think they're just guessing, your most likely belief a priori is that parameter W is 0.5. It's 50% probability on each trial. And so this might reasonably reflect your prior beliefs for these data. Okay. All right. And now what you'll see here is the highest value of this prior is here, and then the belief or the probability decreases as you go away from W, and it decreases linearly. Okay. So maybe you like that one. Maybe you don't like that one. Maybe you have something against curves with a sharp point on them. There might be reasons for doing so. So let's look at one that doesn't have quite the sharp point but has the same characteristics. I'm going to call this one the smooth peaked prior. And again, I just made this up before the lecture. So I can choose anything I want as long as it is a probability distribution. Okay. So this one is, okay, it actually has a name. It's called a beta distribution. We can talk more about that a little bit later this semester, but it is a probability distribution. Just like before, its most likely value a priori for W is, again, at 0.5. Now, again, this is a good skeptic's prior. Okay, the highest degree of belief is that is that W equals 0.5, and that belief decreases as you go away from it toward 1 and toward 0. Okay. So the question I have is, so we're supposed to use these priors and multiply by the likelihood to get the posterior. How does this affect what the posterior looks like? So I took the liberty of doing this in R already. Now that R code is posted in the description below, as well as on Canvas if you're in the Canvas course. And you can use that code if you want. There's a lot of it. My goal in this lecture is not to go through the R code, but if you do have some experience with R and want to get into that, certainly by all means, dig in. So the idea behind our Bayesian updating is this. It comes directly from Bayes' theorem. To get the posterior distribution for W, we multiply the prior, okay, so one of those three curves that we just posted, and the likelihood, so the binomial function. And then of course, we have to divide by a constant so that the area under that curve is 1. That's that probability of data thing that we looked at. And so here's the result from R for each of these priors. So I'm actually just going to make a little table that plots the prior and the likelihood and then the resulting posterior. So here's the first one. Here's what this looks like for the flat prior. Okay. Now I want to point out something here. What do we mean by multiply? Well, what we mean is for every value of W, you multiply the value of the prior times the value of the likelihood. So in this case, this would be 1 times 0. And here, it would be 1, right? The height here is 1, times a little bit more than 0. Here in the middle, this would be 1 times whatever that value is, all the way out here to 1 times this value. Okay. Now the point is here's something that's really kind of happening. Notice that every point along the likelihood, every value that you get gets multiplied by 1, which means it doesn't change. That's why here the posterior looks exactly like the likelihood. That's because a flat prior does not change the likelihood. All it does, you'll notice the scale on the y-axis is a little different. All it does when we go through this process with Bayes' theorem is it changes the heights of things, but it doesn't change the relative scale of, it doesn't change the relative heights of them. It simply changes the area under this curve. So now the difference between this curve and this curve is this one has an area of 1 underneath. That makes it a probability distribution. This one does not. Okay? But by virtue of doing this computation, we get a probability distribution. And we'll talk about how to use that in just a second. But before doing that, let's look at what happens when you use different priors. So for prior 2, it wasn't flat. It was peaked right here, right? And it looked like that. Let's see what that does to the posterior. Now you might think immediately, well, it doesn't really do much to it. But if you look more closely, you'll see that it does change the nature of the posterior quite a bit. Let's look at that. Okay, so again, how does the multiplication work? You take every y value here and multiply by the corresponding y value along this likelihood. Now what that's going to do, let's compare this posterior to this posterior. You'll notice that once you get past the peak, right, it decreases. For the first one, the decrease is relatively smooth. But for here, you'll notice there's like a corner point right there. Because what's happening is this decrease is getting multiplied by a linear function. And so it's sort of inheriting that linear shape. It's almost like you've got a, smooth increase and then boom, straight down. No gentle curve whatsoever. As a roller coaster, this one would be a lot more exciting to ride than this one. So there is a slight difference in the posterior distributions that you get when you use this prior versus this prior. Now we'll see that for sure when we actually start quantifying our uncertainty on these estimates here in just a couple of minutes. Let's look at one more result. The last one was that smooth peaked prior. Okay. And you can see it's now, this posterior has retained a bit more of the smooth nature. It's hard to see them both up here. Let me shrink this down just a little bit. It's hard to see them both. They don't look appreciably different, right? This one and this one look very, very similar. But again, I assure you they are similar they are different, as you'll see in just a moment. So as I mentioned, you'll notice that those posteriors are similar, but they're not the same. So to see how they are different, let's do something that might be useful to us. Let's look at the median value and the interval of values W that contain the middle 95% of the distribution. Okay, this is, by the way, this is the reason I'm choosing this, is this is something that you'll see a lot in Bayesian statistics. This is called a 95% credible interval. It's literally the middle 95% of the mass of the distribution. So again, I did this in R, but let's look at the results. So for the uniform prior, remember, this one looks just like the likelihood function, looks just like a binomial function. Okay, you'll see that the median of this distribution is 0.453. That's really close to the 45% that we would get from 9 divided by 20. Okay, so that's not too surprising that the median value is here. These two values here, 0.257 and 0.660, these are the outer endpoints of your 95% credible interval. If you were writing this in a paper, you would say something like 95% credible interval, CRI, equals, and let's put those numbers down, 0.257 up to 0.660. So you may have heard of confidence intervals before. They're kind of a weird concept, but this is just literally, there is a 95% probability that the value of W is between those two numbers. That's pretty darn easy to interpret. Now let's look at how this changes for the second one, the sharp-peaked prior. Now, notice the numbers are different. The median for this one is actually a little bit bigger than 0.445. It's 0.464. And you'll also notice that the endpoints are drawn in just a little bit. Instead of going all the way out to 0.257 on the left, this one, the left endpoint, is at 0.278. And this one's a little closer to the median as well, 0.648. So you actually get a tighter interval when you use this sharp-peaked prior. What that means for us is that uniform priors don't give you as much what's called regularization or as much shrinkage towards your estimate as a more considered prior does. So I would caution you against using uniform priors in practice. But I'm getting beyond the point of this. Right now, the point is just to notice that the prior has an impact on your estimate. The medians are different, as well as the 95% credible intervals. Finally, let's look at the third one. The third one was the smooth-peaked prior. Given that it's not as sharply decreasing around 0.5 as the sharp-peaked one, it probably has an estimate somewhere in the middle of these. And you'll see that's exactly what happens. We get, once again, close to 0.45, and then these values are somewhere in between the extreme estimates that we got as far as the 95% credible interval. So again, the point of all of this is that even though the posteriors look very similar, the choice of prior has a small effect, or sometimes an even bigger effect, on our posterior estimates of W. What does that mean? Is that just an academic exercise? No. First of all, choosing the best prior to use is something that's not trivial and is an active area of research. So I have colleagues who do this kind of stuff all the time. And you'll see papers where the main point of that paper is to demonstrate that using this prior works across a large class of problems in this discipline with these types of constraints. And that's a good thing to know, because as analysts, I mean, we're not always going to be able to think of the best ways to do things statistically, because often we're methodologists in terms of experimental method. And so if you have really good work that demonstrates that a certain type of prior works for these kinds of things you study, then by all means, that's what we should use. And then more importantly, let me just say that when you're reporting a Bayesian analysis, you must always report the prior that is used. Let me grab my pencil real quick since I just threw it on the ground. So you can't just put whatever the results of the Bayesian analysis are without also placing it in context. You must be able to say, here's the prior that I used. Okay. So let's conclude by wrapping up our discussion of inference. We talked about estimation, of course. But what about model comparison, right? Which model best predicts the data that we saw? Well, one way to consider this is let's start by writing Bayes' theorem for two models. both H0 and H1. So of course we can do that. We know the form of Bayes' theorem. Remember, Bayes' theorem is posterior is the prior times the likelihood divided by the prior predictive. And we do that for H1 as well. Posterior equals prior times likelihood divided by prior predictive. Now what I want to do is take those two posteriors and divide them. That is, I want to compute the posterior odds. Okay, anytime you take two probabilities over each other, that's called odds. So if I take the posterior probability of H0 divided by the posterior probability of H1, well, that's going to be this one over this one, okay, times this thing over this thing, right? This thing over this thing. Now that looks really complicated, but you might notice that the denominators of those two fractions are exactly the same. So we can divide them out, which leaves a little bit simpler representation. Okay, something like this. And I'm going to give this last one here, these two likelihoods, this likelihood ratio, if you will, I'm going to give it a special symbol that might be familiar to you already. And I'm going to jump ahead to the slide, but it's called BF because this is a Bayes factor. This is the factor by which these prior odds are updated to give you the posterior odds. Okay? So what do we have? We have that the posterior odds are equal to the prior odds times this updating factor. Okay? And that updating factor, probability of data given H0 divided by probability of data given H1, is called the Bayes factor. Now I want to introduce Bayes factors today, but I will promise you much of this course, in fact most of it from here on, will be spent learning how to compute and interpret these Bayes factors. But today I can give you a couple of plots that will make it easy for us to see what the Bayes factor is for our example. Okay. So let's look at our example. Remember, in our example that we led off with, we observed 9 successes in 20 trials. And so that was the observed data. For our models, we had a binomial likelihood. We set H0 as W equals 0.5. Remember that there's no effect, that there's just a 50-50 chance on each trial of getting a success. And then the alternative model is, we're going to make this a little simpler. Instead of doing a directional one, I'm just going to say that W is not equal to 0.5. Now, in a Bayesian context, you must then specify how that parameter W is distributed a priori. That is, you must place a prior on W under the alternative hypothesis. So what I've done below is I have taken a really neat idea from Alexander Etz, Julia Hoff, Jeff Rauter, and Joachim van der Kerkhoff. They had a paper in 2018 basically that says here's how to do Bayesian inference for any hypothesis you can specify. And one of the neat things they did in this paper was introduce the notion of a predictive distribution. Now, what a predictive distribution is a little bit complicated for this lecture, but intuitively what it shows is the data that we would expect for each model weighted by the prior probability for all values of W. So it's essentially a Bayesian version of seeing one of those probability distributions that we did in lecture 1. Essentially, it takes that binomial likelihood and then weights it by the prior for the model that you're considering. So again, I did this in R. You can see that code in the description below, but let's just look at the outcome first. Okay. So first of all, you have to specify the prior. So let's use the uniform prior first. And so the way this plot works is it presents two bar graphs kind of on top of each other, but one of them is flipped down below. So even though it's negative down here, this is just upside down. Okay. So the top one, this is under a uniform prior. These are the data we would expect under H1. Okay. In other words, we would reasonably equally expect any number of successes to be observed from 0 up to 20. But under the under the null hypothesis, W is 0.5 exactly. So what you get is exactly the binomial likelihood. The most likely data that you would observe is this one right here. And then these arrows represent the data we actually observed. Okay, so remember, we observed 9 successes in 20 trials. So this tells me the probability of observing that data up here under H1 is this, 0.0476. The probability of observing that data under H0 is 0.1602. Now remember, in model comparison, we ask which model best predicts the data. And you can see here, this model, H0, is the best predictor of the data because its probability is higher. So the next natural question is, how much higher? Well, the Bayes factor is what gives us this. Remember, the Bayes factor says take the probability of the data under one model and compare it to the other. Well, we have those probabilities here. The probability of observing 9 successes under H0 is 0.1602, and the probability of observing that data under H1 is 0.0476. Simply divide these and you get a Bayes factor of 3.36. And the way we would interpret this is very simple. It says the observed data are 3.36 times more likely under H0 than under H1. This is direct support for the null hypothesis. Let's do the same thing for the smooth-peaked prior. The only difference here is the prior that we use to quantify the uncertainty in W under the alternative hypothesis. So these are the this is the expectation on the data if W is not 0.5. Okay, and again, this is the expectation on the data if W is 0.5, the null hypothesis. Once again, these arrows point to the observed data, and these give you the relative likelihoods of that data under the two models. So the Bayes factor, once again, is relatively easy to compute. The probability of the data under H0 is 0.1602. The probability of the data under H1 is 0.0678. Divide those two, you get a Bayes factor of 2.36, which we would interpret as the observed data are 2.36 times more likely under H0 than under H1. Okay. Now you'll notice one of the neat things about this kind of diagram here is it gives you the relative support for all the range of data, right? So the data we observed was x equals 9 successes. But suppose that you observed, let's say, 14 successes, right here. Let me put a little mark there. That's 15. Let me move that. Let's suppose you observed 14 successes. Now in this case, you can see that the probability would actually be higher to observe that under H1 than under H0. So you could modify that R code that I have and actually find those probabilities. I won't ask you to do that in any homeworks here, but you certainly could. The main point is that conceptually you can see that the Bayes factor depends on the data you observe, right? It is a direct function of the data. So data out here is much more likely under the alternative, which makes sense. If you're seeing this many successes, chances are really good that they're not guessing, right? That there's something more than guessing. And again, the same thing down here as well. So that's what a Bayes factor is. A Bayes factor is simply the relative likelihood of the data under the two models. So let me just end with a little postscript. You may be wondering how I generated these plots. There's a lot of plots that we use today. And I want to assure you, don't worry. The goal today is not how to do this in R. We would be here for hours if we were doing that. The idea and the goal that I have for us today is to introduce the concepts and the language. We will begin discussing computation of Bayes factors in the next lecture. I'm really excited. This is going to carry us through the entire course just with that, what seems like very limited topic, but there's a lot there, and we're going to have a lot of fun with it. So that's all for today. Work hard, look at these plots, see if you can figure out what they're saying. Let me just say, if you haven't before, this is a great paper. Okay, so take a look at that. I'll put a link to it in the description below as well. So until next time, when we start looking at computation of Bayes factors, I'll sign off and we'll see you then.